So a couple more examples of being able to evaluate these line integrals. And this time what we're going to see is that the functions are not parameterized, or the parameterizations are given this time, but the differential is not ds, it's actually in terms of one of the three given variables, x, y, and z. So a fairly easy example is that we want to evaluate the line integral x cubed y squared z dz, where c is the path x equal 2t, y equals t squared, and z equals t squared. And the range of values is going to go from 0, 0, 0 to 2, 1, 1. So the first thing we see is that we need to find what the value of t is. Now t in this case is going to be 1, and here's why. What we're going to do is we're going to say that 2t is going to be equal to 0, okay, just by setting this up, and also 2t is equal to 2. And that gives us that t is 0 and that t is 1. All right, so t is going to be 1 for this bound, and t is going to be 0 for the lower bound. All right, now that's just for the first one. We also have to verify that for the other two. All right, so I'll just randomly suggest that t squared equals 0, t squared equal 1, and again we get that from right here if we're looking at the y variables, and again that just gives us that t is equal to 0 and t is equal to 1. All right, so those are going to be the bounds in this case. It's not always going to be 0 and 1, but in this case it is. The other thing we're going to do is we're going to find dz. All right, so dz dt is going to be equal to 2t dt. And all we're going to do at this point is we're going to substitute for all the other variables. All right, so our integral is going to go 0 to 1. We have x cubed, which is 2t cubed. We have y squared, which is t squared squared. We have z, which is t squared. And then instead of dz, we're going to substitute 2t dt. Right? At this point, even though there's a lot of factors going on, it's not a difficult integral. We have 3 2's from the 2 cubed, and then we have another 2 from the 2t, so we're going to have a 16. Right? And then we have 3 2's, 3 t's and 4 t's is 7 t's, 8, 9, 10 t's. All right, so we have t to the 10th dt. That's going to be 16 elevenths to the 11th, or t to the 11th, and that just gives us 16 elevenths. All right, so that's a fairly easy example. A little bit more difficult example is when we have this sort of thing, where we have a region that's consisting of different line segments. Right? So C is going to consist of 3 line segments, 0, 0, 0 to 0, 1, 1. 0, 1, 1 to 1, 2, 3, 1, 2, 3 to 1, 2, 4. Right? In this case, what we're actually going to have to do is we're going to have to compute 3 line integrals, and then we're going to get the sum of those to be able to figure out what the overall line integrals evaluation is going to be. So C1, path C1, we could parameterize that. Now clearly, x is equal to 0, right? Because we notice that we go from 0, 0, 0 to 0, 1, 1. We could say that y is going to be equal to t, because it goes from 0 to 1, and that z is going to be equal to t. And again, t is going to range from 0 to 1. Each of the derivatives, dx dt is 0, dy dt is 1, dz dt is also equal to 1. And what we're going to do is we're going to substitute back into the original line integral. So now we're going to have integral 0 to 1. We have z squared, so that's t squared times dx, which is 0. We have minus z, which is t times dy, which is 1. And then finally we have 2y, so that's going to be plus 2t, and then dz is 1. And all of those are integrals with respect to t. Right? This is actually fairly easy because if we go through and simplify this, we just have the integral from 0 to 1 of just t dt, and you can very easily work that through and end up with a half. So that's for path C1. A little bit tougher might be some of the other paths. Okay, so now we're going to take a look at C2. Okay, so path C2, we're going to say goes from 0 to 1 on the x coordinate, so that's just going to be t. From 1 to 2, so y is going to be equal to 1 plus t. And then notice that finally we go from 1 to 3, so z is going to be equal to 1 plus 2t. Right. Now we have to keep all of the integral bounds the same, 0 to 1 in this case. If they're not, then unfortunately when we get to the answer, it's not going to be the same line integral, at least the same interval for the line integral. Right. So we know dx dt is going to be 1, dy dt is also going to be 1, and then dz dt is 2. Right. We're going to substitute, all right, and I'm just going to copy this down. So C2 is going to be the integral, or the integral for C2, excuse me, it's not C2 itself, 0, 1. Now z square we know is going to be 1 plus 2t, so that's going to be the quantity of 1 plus 2t square, dx, which is 1, plus, or minus, excuse me, z, which is 1 plus 2t, times dy, which was 1, and then plus 2y, so 2 times 1 plus t, I believe, times dz, and dz was 2, and then we have a dt. Alright, so even though it looks like it's going to be a little bit of a pain, it won't be all that bad. All we have to do is just take care when we're doing our evaluation. Alright, so when we compute, we're going to end up with 1 plus 4t plus 4t squared minus 1 minus 2t plus 4 plus 4t, and there's a dt in there. Right? So FOIL distributed, all that good stuff. Integral 0 to 1. So we have a 1 minus 1. Those are going to cancel out. We have 4, 4, and negative 2. So that should be a 6t. We have a 4t squared. And then we have a minus 2. I'm sorry. We have a plus 4. So that's our dt. So plus 4. And then if we evaluate, that's going to give us 3t squared plus 4/3 t cubed plus 4t from 0 to 1. And if we compute that, we get 3 plus 4/3 plus 4, which is going to give us 25/3. Finally, we have one more to do. So now this is going to be the easiest of them. So we go here. Same problem. Right. So for path C3, we're going to parameterize it. So for path C3, x is 1, y is 2, and z is going to be equal to 3 plus t for the parameterization. Both dx dt and dy dt are equal to 0. And then dz dt is going to be equal to 1. Right? So it actually turns into a very nice sort of integral, because when we evaluate it, the first two of the expressions contain a dy and a dx, so they just go away. So in reality, we just have integral 0 to 1 of 2y, so that's 2 times 2 times dz dt, which was 1, and that's the integral from 0 to 1, there should be a dt here, of 4 dt, which is just going to be equal to 4. All right. Finally, we're just going to add all the paths together. So C1 plus C2 plus C3. If we go back all the way to the beginning, we remember that 1/2, 25 thirds, and 4. So we have 1/2, 25 thirds, and 4 are going to be the three values. And we end up with 77/6 as the total line integral. All right. So now that we know how to evaluate line integrals, the next steps we're going to take are to be able to utilize them in some sort of real-life application.